Hi Bobcats. In this video we're going to take a very brief peek at a theoretical approach to entropy, and we're going to be looking at how particles can be arranged into different positions and the entropy that's associated with those arrangements of positions. This is laying the foundation for more advanced work in a physical chemistry class, so that when you see this idea in CHEM, it's not the very first time you've ever run into it. So we're just taking a very brief glimpse at it here. Our objective is to start to develop a qualitative understanding of the relationship between entropy and probability. So Boltzmann proposed this equation that the entropy of a state is given by K, which is called the Boltzmann Constant, times the natural log of W. All right, so K has a numerical value of 1.38 times 10 to the negative 23rd joules per Kelvin. K was derived by taking the ideal gas constant and dividing it by Avogadro's number. Notice our units, though. We have to use the joule value of R to get there. So if you take 8.314 joules and you divide that by Avogadro's number, you will end up with the Boltzmann constant. W is the number of equivalent arrangements of the particles called microstates. W is given by this equation x to the n, where x is the number of locations available and n is the number of particles. So just to give you an idea of what we're talking about here, and these diagrams down at the bottom are illustrating the arrangement of 3 particles over 2 locations. The locations are the top and the bottom half of the box. The 3 particles, well, one of them is all black, one is black with a white outline, and one is black and white striped. We could put all 3 particles into one position. We could put all 3 on the top, or we could put all 3 on the bottom. That's what's illustrated in the first 2 boxes. Then in the next set of boxes, we're putting 2 particles on one side and a 3rd particle on the other side. And then in the next 3 boxes, we're repeating that pattern. We're just flipping the roll of the tops and the bottoms. And so we're just looking for how many different ways we can arrange these particles in these 3 particles in 2 positions, and it turns out the number of ways that we can do this becomes x to the n, where x is 2 because we have the top and the bottom of the box, and n is 3 because we have 3 particles. So we have 8 possible arrangements. And if you count up our boxes here, we've got 8 of them. All right, let's calculate the entropy of the system from the previous slide. There are 3 particles arranged among 2 positions in those diagrams. So to calculate the entropy, S is equal to K times the natural log of W. We have a number for K already, and W is x to the n. So x, well, let's see, the 3 is the n, and the 2 positions make the x, so that's 2 to the 3rd, or 8. So this equation for entropy is K, which is 1.38 times 10 to the negative 23rd joules per Kelvin times the natural log of 8. Now remember, when you run this through on your calculator, you want to use the ln, not the log. So 1.38 E23 negative times 8 natural log And that tells me that the entropy is 2.87 times 10 to the negative 23rd joules per Kelvin for those 3 particles arranged in 2 positions. Let's relate these ideas back to the previous video where we were more concerned with the sign of S, of delta S. So if we start with 2 particles arranged in 2 separate positions, and we end up with those 2 particles arranged in 1 position, we have a decrease in entropy as those particles become condensed into just 1 location. So delta S here would be negative. Delta S for this transition would be less than 0 or negative. So our objective here was to look at the relationship between entropy and probability. The more ways there are to arrange particles, the greater the entropy. And let's see, so our equation was that S is equal to K times the natural log of W. K is the Boltzmann constant, which is 1.38 times 10 to the negative 23. And that's joules per Kelvin. And W is equal to x to the n, where n is your number of particles, and x is the number of positions that are available to those particles.